In this project, we will demonstrate the implementation of public key cryptography using the elliptical curve cryptography algorithm, also known as ECC. Public key cryptography is an encryption method that uses a paired public and private key algorithm for secure data communication. The public key is used to encrypt and the private key is used to decrypt. After careful consideration between the Diffie-Hellman technique and the Evermore technique, the Evermore technique was selected. We will now illustrate the Evermore technique using a Python program.
For our detailed procedures and steps to actually creating our program, we dedicated a lot of time to researching what we were actually supposed to implement, and that is an elliptic curve cryptography, or ECC. With that, we conducted about 1 week and a half of research dedicating on different systems, techniques, and different methods that are used to implement an elliptic curve cryptography. The team then looked at the design of our code and what language we would like our code to be represented in. Using that, we were able to come up with a structure of where our code would begin in terms of collecting data from a user and where it would end, which would be a decrypted plain text message. Python was selected as our programming language because of its simplicity to allow us to develop the program at a faster rate to meet our 5-week deadline for the project. We wanted our program to be executable on many different devices and on different platforms, versions, and so forth. So we decided we would execute our Python code in command prompt. With this, the team conducted several testing and found out that with our original elliptic curve cryptography implementation program, the looping algorithm added a significant amount of time to the decryption of a message longer than 3 characters. That caused the team to have to wait an average of 3 hours if a plain text was entered over 3 characters during the testing process. So we went back to the drawing board and revised our looping algorithm for the Python code. A 40-character message could be encrypted now in less than 15 seconds.
Now let's do a live demo.
Okay, this is Nazma Bandla. I'm going to explain the Python code we used for implementing elliptic curve cryptography. So basically, the elliptic curve cryptography is an approach to the public key encryption based on algebraic structure of elliptic curves over finite fields. So ECC is difficult to explain compared to other methods. So the main function of ECC compared to the other public key and cryptographic is that it uses smaller key and provide equal security as other public key cryptographic techniques. So because it uses the small key and the processing overhead is much lesser compared to the other techniques. So basically, elliptic curves are not really ellipses. They are named because it was described as cubic equations similar to that of used to calculate circumferences of the ellipse. So the basic the equation of the ECC is this one: the y square equal to x cube plus curve point constant in x and the curve point b. So basically, we need several constant variables here. So the curve being the prime number in the curve, and these are the curve A, curve B, or variables on the curve. These are basically points, and B point is a generator point, and in this, B and Y, Bx and By are coordinates on the curve, and these are the coordinate values we choose in this program, and these are the small functions to encode decode the original text message. And here, this portion, it converts the original text message to the hexa integer value. This is used during the encryption process, and this one is to reverse it, from hexa integer value to the real text. And this method, this function, will be used in decryption method. Okay, and this is a private key variable, so we can replace this value with any other value, because this is a private key. And the public key, this is a public key generator. Now we can this one calculates and generates a public key using generator points here, and the private key. And these are the curve points. These are the points, coordinate points on the curve. And this is original message that we're going to send. And here it converts the message, the original message, to the hexa numeric value. And here, basically, we are printing this original value. And here, coordinates, the coordinates being used, these are the initial coordinates for that particular message. And this is the function used to do the calculations. Basically, this whole thing involves the main functions. One is modular, inverse, and point addition, and the double and add. Okay, and what actually does is that in the modular inverse, so it has the divisions in elliptic curve. So this is actually not the division, but it's kind of division, modular division. So basically, in the modular arithmetic, we do not have a division operations. So, however, we do modular inverse, so the values inverse will always will be the equal to 1. So we do modular value in the divisions here. So here the point addition is these are the distinct points, 2 points in the different points of the coordinates, and this is to construct the line between the 2 points. That is called the third point on the intersection of the curve. So this helps in giving the intersection point on the curve. So it uses these calculations, the doubling and the addition, and again inside that it uses modular inverse, and doubling is the similar to the multiply and square in modular, the exponential equations. So it uses all these, the calculations within this algorithm, this program implementation. So, and then where were we here? Okay, we're up to here. Yeah, it uses this calculate double and add calculation to generate the initial coordinates on the curve, and these are the points. It prints the initial coordinates, and here it starts the encryption process. So here, this is a random number. This can be this is used in encryption and decryption process. So if you look at this one in here, the encryption cipher text encryption starts here. So in this point, if you look at this one, this is a random key where we use a random key to cipher the text. This is the encryption process, and here the encrypted message, the coordinates are here. Okay, so these encryption coordinate points are displayed. Coordinate points are generated here with these calculations. And decryption portion starts from here. And again, this one, this is the original message. And then original coordinates and the encrypted message. Okay, and the decryption process starts from here. So and again, it uses the point addition calculation to generate the latest the points, and this portion extracts the original text message. It means decrypting the original message from the encryption. So again, this uses the point addition calculations, and after the extracting the message, and it converts the hexadecimal information into the real text. So real text, this function is explained here. The converting the hexa integer to the text, and it means basically it decodes the original message. Okay, and here, and it is printing the decrypted message. And this is the whole program for this implementation and the Python code. And for this one, we installed the Python software with version 3.7.3. And yeah, if you look at this one. Okay, and this is a Python, the Python console. And here, if you open this one, the command prompt, and so I'm going to the I'm directing to the Python module where Python executables are. C drive, program files, and this one. Okay. And okay, so in this directory, so this is the Python executable code. So, but, this is my original Python code for ECC, and this is located in this directory. Okay. To C drive, users. Okay, and this is the code, my Python code. Okay, and let's go back to the executable location, the Python code, Python executable module, and type Python, and this is where my Python code located, and this is the Python code, and run it. Python. Okay. Okay. So this is the execution result. So here I executed the Python code, and it says now the public key generation starts here, and this is the public key coordinates and other points on the curve, and so message being sent through this technique is, hello class, welcome to the CST 615 course, and this is here. Okay, the message is here. Yeah, here. And the public key, like I mentioned, the public key here is public key is generated with this calculation. Okay, and here the hexanumeric equivalent for this original message is here. This is the hexanumeric equivalent. And the original coordinates are located here. These are the original coordinates, and the calculation for this one happens with this call. And encryption process starts from here, and here, like I mentioned before, we choose the random number to generate the coordinate points on the curve. The encrypted ciphertext of points, pair of points. This one and this one. Oh, sorry. This one. No. These two pairs of ciphertext. These are the encrypted text on the ciphertext located at these coordinates, and the decryption process here. Okay, the decryption and the decrypted coordinates are these ones. Yeah, if you look at the original coordinates at the before the encryption, these are the original coordinates. The message located at, and after the decryption, And these are the decrypted coordinates. Those are equal, and this is where the message surrounded it. And this is the decrypted message. This is the original message that we sent, showing up after extracting as part of the decryption. And yeah, and that is about this project execution. And again, the first step, it generates the public key, and this is the text being sent. And these are the coordinates where the text centered at. And again, the encryption process here and decryption process, and this is the extracted message. And yeah, this is all about the execution of the ECC.
With any good project, you're going to have some surprising things that come unexpectedly. During our project, we found in the researching phase many elliptic curve cryptography systems and techniques derived from the same Diffie-Hellman key exchange process. This was interesting because Diffie-Hellman was one of the top runners of how we wanted to implement our elliptic curve cryptography. And we actually settled on a technique which combines additional factors but still holding on to the true core of a Diffie-Hellman key exchange, called the Elgamal technique. As mentioned before, the most surprising thing for us is changing one algorithm, which was our loop algorithm, could significantly decrease the amount of time spent decrypting a plain text. The longer the message of the plain text that needed to be encrypted also changed the random key and public key that was generated with our algorithms in the Python program. We believe that the length of the public key and random key not only correspond with the character length of the plain text being encrypted, but also with the amount of time it may take for the program to actually be executed. At least that was the perspective and the theory based off of our old loop encryption, which took up to 3 hours to decipher a 3-character plain text. With the new loop, no matter how long your public key is, the estimated completion time is not relevant. A 40-character plain text encryption on the new loop algorithm can be done and decrypted in less than 15 seconds.
With any project, you will have areas of difficulty. In this particular project, we identified resource management and the technical approach. With the resource management as a collective, we had varying levels of experience with encryption as well as coding. We had to be intentional about leveraging our strengths. Secondly, regarding resources, we had to account for the group members' individual circumstances. We had to account for our locations, vocations, and other personal obligations. We were able to overcome those challenges through careful planning and execution. Lastly, regarding our technical approach, significant time was spent in research, understanding, and implementation. With the research, we explored the principles of elliptical curve cryptography, and we found the approach that would best satisfy our requirements. The research took us through the evaluation of various crypto systems, i.e. Elgamal, systematic encryption, asymmetric encryption. When it came to implementation, we decided that the Python language would be the best option. Python is a high-use and effective programming language. We had members that were familiar with Python, and the team was able to get to a working knowledge of the Python language.
Okay, for team contributions, I'm going to start off by saying what each person did. So Shudan planned the weekly meetings and put together the base template for the weekly progress report. She also helped test the program to ensure that it was of great quality. She also created meeting codes for us via WebEx, so each week we knew what time we were going to be joining the web. She also projected her screen so that we can all be on the same page. Omar tested the program as well to ensure quality, and he contributed with the program code. He also contributed to the discussion in terms of what coding programs we were going to actually use. Gloria constructed the project introduction. She helped format the weekly progress report, and she's also the one that submitted the first weekly progress report. I, Nakia, detailed the team contributions, and I submitted the second week project report. Marichima developed the code in between meetings and helped format it. He came up with the correct format, and then also constructed the code on Python. As a team, we ran the code to make sure it ensured properly and that it could be ran on any computer via command prompt. We also discussed as a team like what time and dates was going to be best for us to join the meetings. And then we looked at the weekly progress report for the week before so that we can ensure that we're staying on track and make sure the project is done on time. And that's it for team contribution.